seeing the right version of the slides or the presenter's version?
Nope, we're seeing the presenter's version. Or I mean, sorry, yeah, the right version.
Right. Okay. Perfect. Perfect. Thank you very much. Okay. Yeah. Thank you very much for the nice introduction. So yes, I'm Christopher Lane. I'm right now a staff scientist at Los Alamos National Laboratory in New Mexico. And so it's been very dry and nice lately. Probably similar up in New York, where I come from. I actually grew up about an hour south of RPI. And so today, yeah, I'm going to talk about some recent advances in density functional theory that we've been pushing forward. And really, it's making towards a first principles treatment of complex correlated materials. And so probably in some of the other talks you've seen where we've talked about maybe DMFT or these various other sort of corrections to DFT, here we're going to show that maybe there's some new functionals that allow us to really start to explore these correlated materials without introducing sort of new corrections on top from many-body theory. And so that's where we're going to be headed over the course of this talk. So the main first thing I want to do is sort of acknowledge and thank my different collaborators I've had. And if you can see my pointer, let me just make this red here. There's a pointer. Here we go. So just to thank my collaborators, this is really a joint effort between myself at Los Alamos and the group of John Wei-Sun at Tulane University in New Orleans. We also have Bernardo Barbolini and his postdoc Johannes in Finland at Lappeenranta University. And then also the group of Arun Bansal, where I actually did my PhD at Northeastern University. And so we still have very close, strong ties. And here it's a nice collaboration because we get to combine people's knowledge on theoretical spectroscopy, the density functional theory, and also particularly for John Wei, who actually does the construction of these different functionals themselves. So we really like to span a large swath of condensed matter physics and really trying to address real materials, their spectroscopies, and their different functional uses in either batteries or solar cells or in fuel cells also. And so really it runs the gamut into whole different types of ideas that we like to explore. And just to sort of thank our funding sources, we have those from Los Alamos, the LDRD program, so it's our in-house funding source, the NNSA, which of course supports the lab particularly, and then those from the Department of Energy, the CCDM, which was an EFRC in Temple University, some money from the European Cooperation for Science and Technology. They're really boosting research on superconductivity, which is one of our main interests, and also NERSC for many of the computational needs that we have. And so this is sort of the background of where this is coming out of and the group of people that is driving this forward. And so as an outline today, because this I've noticed on the list that we have talks spanning from lattice QCD to DMFT to sort of all different ranges of physics, I want to give sort of a background on, well, what is the basics of electronic structure theory? Well, what are the main questions that we are concerned with? So not necessarily the particularity of maybe the methodology, but really because we have a good mix of students, what is the main ethos of the field? What are we trying to accomplish? And so maybe we can walk away with some at least qualitative understanding of what we're trying to do. And maybe if this area interests you, maybe you'll find somebody to work with, or you can always contact any of myself or any of my collaborators. And I'm sure we always have our great need for summer students and postdocs and things like that. And so we're going to go over basics of electronic structure theory, the fundamentals of density functional theory itself, so that we can start to see what differentiates it from sort of these many-body approaches. We're going to construct what the scan meta-GGA functional is. So what this new functional we have that's being able to attack correlated materials. We're going to go over at least one case, one study of scan for particularly the sort of prototypical high-temperature superconductor, the lanthanum-based cuprate. And we're going to see, how does it work? What new results do we find? Does it give a better description than what we had before? And so after that, some key takeaways. So specifically, just to really highlight what are the different questions and methodologies, and then some concluding remarks on this particular study that we looked at. So this is where we're going to go. So let's start with first, what are we concerned with? And so the main objects that we're looking at is really looking at novel electronic phases in quantum materials. So what does that mean, first off? Well, we know that we have different phases, so to say we have liquid, gas, solid, and things like that. And they're the main constituent forming those different phases is the atoms or the molecules themselves. So the different kinetic energy or potential energies in the system, based on then temperature, pressure, or number of molecules, will then give you these different phases. And of course, their different phase boundaries are then governed by the different interatomic or intermolecular type interactions. So here, we have a different constituent that we're looking at. We're namely looking at the electron, because now we have that the electron, once we get to small enough scales, the electron, of course, has some Debye wavelength. We've sort of gone from looking at it as a particle to a wave. And now because of that, this is where then the quantum nature really comes out in this object of the electron. And that's where the quantum part comes from. So this is now sort of a buzzword to say quantum materials. But really what it means is that we're now dealing on the scale of the electron and its wavelength effectively. And from that, we have the emergence of many different phases of matter. So in particular, here I just want to highlight a couple of different scenarios to really show you that everything is very similar, yet very different at the same time. And so here for the cuprates, let's say we have, this is some kind of perovskite type structure, particularly you have octahedra of copper, copper surrounded by oxygen and some heavy elements in between to space out the layers. From this, if we add or remove electrons from the material and we look at its like resistivity versus temperature, we find that first off, it starts out as a magnetic material. It's an antiferromagnet. If we dope it far enough, we get a high temperature superconductor. And so this was the real very big discovery that happened in 1986 by Bernoz and Muller. This is really a clear breakthrough that's really puzzling us today. We don't quite know what's going on and the mechanism and so on and so forth still. We have some other phases, the pseudogap, a normal metal, and also some strange metal phase. And so here, really, it's based on the slight doping change, the slight temperature changes. You can go from a superconductor to this pseudogap to an antiferromagnet very, very quickly. And so the main questions that we're concerned with is what is the mechanism for this happening? Why do we get these different phases and how can we describe them? And so here you can see a very similar phase diagram. The very pnictides, another high temperature superconductor. Again, it's temperature for some kind of doping. And then you can also look at fullerides and very similar thing. You can take these sort of buckyballs and you can put some spacer elements in between. And from this, you can drive yourself into different phases. Again, superconductivity is very prevalent here. We have these Jahn-Teller phases, which now means the orbital physics somehow is playing a role, mixing with the lattice degrees of freedom. And so these then sort of benchmark the sort of d-electron, p-electron type physics that's going on. And so they have very similar phase diagrams in some sense. Then we can look at another whole other beast unto itself, and these are heavy fermions. And these are really based on F electrons. So these are using heavy actinide materials. We're now in that whole other part of the periodic table that has to be popped out, and people usually don't deal with those elements because, of course, they get quite nasty very quick, and most of them are radioactive. That's sort of a byproduct. But these, again, also have very interesting phase diagrams. Usually with pressure and temperature, you have antiferromagnetism, superconductivity, and some coexistence. And this then carries over to other ones. Helium, we have a superfluid phase instead of superconductivity. We have layered 2D materials that give way now to charge density waves, so periodic distortion of the lattice due to charge. Superconductivity, some metal, and then sort of the most recent surprising discovery that was made, in at least I believe 2018, if you just take 2 layers of graphene, so you flake off some graphene from graphite, like from your pencil, and then you twist them about 1.16 degrees away from one another to create this moire pattern, you arrive at a phase diagram that is very similar to the cuprates. You get superconductivity, you get a correlated insulator, and some other phases that come out if we start to manipulate this. So here, even from the simplest thing, which is a 2D sheet of graphite or graphene, and twist it with respect to itself, you get all these interesting correlated phases of matter that the electrons want to do really funny things. And so the main questions that we are interested in are down here. And they really ascend in complexity in some sense. We have, well, why do these phases happen? So what is the underlying mechanism that's going on? And then how and why do the transition temperatures depend on the specific materials? Because we see here, of course, the cuprates are not like iron-based materials. They're also a different structure. We see very similar physics, but the transition temperatures are, of course, different. And even within the cuprates themselves, you get vastly different transition temperatures just by changing out the rare earth that's in between them. And so these are things that we want to understand. Why does this happen? And then the last question, which is, of course, the most important, and this is really where theory comes in as the main player, is how can we predict and find new materials with even higher transition temperatures? So the main part is how can we predict these things? Now that we've understood them, how then can we apply these techniques to new materials? And of course, in many respects, we're not here yet. We are still trying to understand superconductivity in most of these materials, let alone predict it. But this is where we'd like to head. These are the main questions of the field that we want to tackle. And so this is sort of always in the background of our minds of where to go next. So now that we have sort of the main questions, we want to ask, okay, what theoretical framework can at least move us towards answering these different questions that we have? And so technically, the question has already been answered. And this is done by the sort of many electron Hamiltonian that we have. And this is given in the non-relativistic limit. But we have all the electron dynamics in the system. So the kinetic energy of the electrons, the electron-electron interactions. We also have the lattice dynamics, the kinetic energy of the atoms themselves, of the nuclei centers. And of course, the nuclei and nuclei can see one another since they are charged. And then we also have electron-nuclear interactions, which of course, if we study the hydrogen atom, is the main player. But here, it's really coupling the electrons that want to freely move about the material with those that are maybe more localized. And also these lattice vibrations can couple to the electrons also. And so this is really taking those two subsystems and putting them together. And this is the main description of the solid. And here, just as an illustration of just to gain some pictorial sense of what we're talking about, if the atomic centers are here given in black, and then we have the electrons running around the outside in some kind of sort of Bohr model, let's say, we could just pinpoint a single electron moving through the solid. So we have a single electron here in blue. At some point, it could scatter off of another electron in the material. Because of the Coulomb interactions, it'll mediate the interaction between these two particles, and these two then will scatter. This one will, of course, go off somewhere else in the material, and this will continue on its merry way. And as it goes along, oh, maybe it sees an atom. And it sees some atom, it's going to then have a scattering event off of the atom itself. So from this electron lattice type coupling itself, and it's going to buzz off into another direction. And then the atom itself is going to recoil due to this interaction. Now, this is how the electron goes through the system. We also can have vibrations of the atoms themselves. So they, of course, have little springs connected to one another, and they can then move and distort. And we also have the problem of just the electron being bound really tightly to the core of the atom itself. And so really, this equation and describing the material itself is really spanning many different length scales and energy scales. We have purely atomic physics that's sitting at these tightly bound electrons versus electrons that are able to move very freely and scatter through different things within the material. So we really have large energy scales from those that are strongly bound states to those that are scattering states or plane wave type states, and then everything in between. And so this problem, of course, is very complicated because everything is coupled to everything else in the system. And so, but this equation does describe everything. And so, as Dirac said, that really the main question changes from what is the main description of these physics, but it really then becomes desirable, as he says, to approximate in practical methods of applying quantum mechanics, that these should be developed to be able to start to tackle this problem. So namely, it lies in making approximations of this Hamiltonian to move forward. And so that'll be the main questions. And this is really where all of the work stems out of. Whether you do many-body physics or whether you do pure DFT, or you want to put things together like with DMFT or GW and so on and so forth, you're really starting with this ethos that this is too complicated to solve unto itself, and we need to do something else. And so first off, the first approximation we're going to make is that we're going to assume that the lattice is stationary. And so particularly that because the atoms themselves are very heavy and the electrons are very light, we know that then the motion of the atoms are going to be on the picosecond time scale, whereas the electrons are going to be moving on the femtosecond time scale. And so having these 3 orders of magnitude difference, that means then as the atoms move, the electrons then essentially adiabatically reconfigure themselves. So the electrons never see the atom moving, and the atom never really sees the charge distribution itself moving also, because everything happens so quick. And we separate the problem. And this is called the Born-Oppenheimer approximation. So in essence, we separate out the wave function. We say that there's electron degrees of freedom and lattice degrees of freedom, and we're going to handle them separately. And effectively what we're going to do for the rest of the talk is we're going to assume that the atoms are standing completely still, and we're just using the potential that they generate and have the electrons move within that. There are people that do lattice dynamics. Maybe somebody's going to give a talk on that, but that we won't concern ourselves here with. We're just going to look at the electron properties of this system. So we've now reduced the problem from one set of infinities to another set of infinities, because we have so many different electrons we need to keep track of. And so here we've retained the kinetic and potential energies and the sort of electron-electron interactions. And now we have some potential that we're sitting in. So here is sort of a very nice picture to illustrate this. We have the electrons can hop from point to point to point of the atoms, and they can have different scattering events that happen between themselves. And so this is really what we're trying to describe. And so the first naive thing we can do to really build up to show the power of density functional theory is, well, what is the most naive solution we could do? The naive solution is, well, this is a partial differential equation. We have n electrons. We know that it should be fully antisymmetric. We know all the different ingredients that go inside. If we look at a particular material, let's say silicon, we know what the potential is. We know what the electron-electron interactions is. It's given right here. And the kinetic energy here is given by this derivative operator. So this is just a partial differential equation. We can try to solve this numerically, and then we can see what happens. And so this is possibly what the wave function might look like here in the silicon itself. And then if we try to solve this numerically with some PDE solver, well, we need to discretize it. And so then the wave function goes from being this smooth object to, of course, this sort of fuzzy one. So it's like we're going back to the 1990s. Everything gets a little bit pixelated. And so this is going to be our grid points that we're going to solve this problem on. And so let's think about then if we want to place 5 electrons within this grid. And so if we want to do that, so we have 5 electrons in this 3D space, and let's say we've discretized it as a 10 by 10 by 10 mesh. And let's then try to perform this calculation. We have one grid point, let's say, is equal to 16 bytes. So this is how we're going to code up this problem. And then we're going to solve this with some methodology. But even just thinking about storing the data, well, we have 16 bytes times a 10 by 10 by 10 mesh times 5, because we have 5 electrons. We're already at 16 petabytes. And this is just to store the wave function itself. And so this here, we've already seen, this is quite intractable already at this one, at this crossing. And so just to get more of a feeling of what this means, is that this is 16 million DVD RAM disks, and each one of these holds about 10 gigabytes of RAM. And yes, there was a drive at one point for people to try to use DVDs as RAM in computers for some reason. It had to be quite slow, but we could store it on all these disks, but this would, of course, then measure up to nearly 20 kilometers high in height. And so this is very futile. We're not going to get anywhere solving real materials with this methodology. So as Dirac said, we need to come up with some kind of clever methodologies to start to really approach this problem. So the first thing we can do is we can say, well, we want to approximate a many-body wave function. So let's use single particle wave functions that we have. And so this is where then the different wave function type methods, these are mostly used within chemistry, but But these are the different quote unquote wave function based methods where they come from within this thought process. That we have some many body wave function, and then we wish to approximate it with something, usually utilizing single particle wave functions. So here, the simplest thing we can think of is that, well, we know this is fully antisymmetric. And if we form a fully antisymmetric product of these wave functions, we end up with sort of this determinant here, because we know the determinant is a fully antisymmetric object. And from this, we get a wave function that should at least obey the Pauli exclusion principle. So if R1 equals R2, this wave function will be identically 0 because the determinant dictates that. If we have a row or column that are the same, we must have then that it's equal to 0. And so this is a nice, very nice first approximation. We at least endow it with some properties that we have that we know that should be obeyed by these electrons, namely that they can't sit on the same site due to the statistics. But here we have that this actually doesn't include quote unquote correlation effects. This is really just saying we have uncorrelated single particle wave functions that we're just putting together in a fancy way. And so based on over the years, different chemists and such have developed new approximations to be able to generate new wave functions that really try to embed these different correlation effects. And so here, just for instance, in terms of the configuration interaction wave function, we include the Hartree-Fock, which has all these sort of occupied ground state wave functions that we had. You can include an excited state. You can have them doubly excited or triply excited, so on and so forth. Because here, it's recognizing the fact that the many-body wave function doesn't only include the ground state information. It also includes all excitations and all sort of n-particle correlation functions. So the main thought process is that if we embed more and more information here as to these different processes, we're better approximating this many-body wave function. So it's a constructive way of thinking about how we build up methods that are better and better approximate this many-body object. Now, of course, there's many different flavors of this based on how you want to construct it. The main point here in the slide is that this is still a 3n object. You're still scaling with the number of electrons in your system. And so at some point, this methodology is going to start to break down. Because as we know, computationally, we're limited based on the memory, based on CPU timing, and so on and so forth, and also the number of cores we can have on a single system. And so at some point, there's going to be a limitation that we can do practically. And so here it ends up being around 100 electrons. And to gain some sense of that is really to think about if we have n electrons and m basis functions, well, it's an m choose n. This is sort of the number of different wave functions we need to describe the system. And so if we do this for simple numbers, just like we did before, we need about 10 to the 9 different determinants again. And so this is blowing up really, really quickly. And to save this in memory, of course, is a nightmare. And so we really need to think differently. And so we've gone from this problem of having all these approximately 10 to the 23 different electrons in the system. We've been trying to sort of follow our nose to figure out some methods that might work. But really, we need to find something completely new. We need to think about the problem differently so that we can have something that's computationally tractable. And so this is when we really need to think about some new directions. And so we're at a crossroads, really. We have wave function-based methods that still contain all the endpoint correlations between all the different particles in the system. And so really, if we have this electron up here, it's still coupled to all the other electrons in the system. And let's say they're sitting in some potential here. So really, by calculating this wave function, you contain all the information. And even out to sort of the 30-second correlation function of this object. But if we really think about what we want to calculate, we want to be able to calculate the total energy of materials. We maybe want to calculate what is the relaxed structure of the material. We want to know the charge density, and just at a minimum, the ground state properties of this. So there's really no reason we need to retain any of the higher order information. Really, we probably need, well, what is the density? So that's then would be then the sort of single particle correlation. And we maybe need 2-particle correlation if we want to look at some simple excitations in the system. But beyond that, there's really no need to keep all this extra information around to be able to make progress in predicting and trying to explain these interesting materials. And so that's the main idea of then picking a different path, namely finding some reduced quantity that will describe our system to the best of our ability, of course. And so here, for instance, maybe we could pick the density. Instead of saying we need to know, of course, the correlation between all these guys, we just need to know what is the aggregate density of the single particle here. And that maybe is enough to be able to deduce some observables that we have in the system. And so this is really where the new thought process comes from. How do we make our thinking simpler? And so here I've just sort of produced a list of some reduced quantities we could choose. And there are various different sort of computational and numerical efforts also. So first off, we could use the particle density like I mentioned. It's very simple. This is just a 3D object, and it just depends on how much we discretize the space. It doesn't depend on the number of electrons in our system because it's just a single particle. And so this object is very simple. It can fit on the disk. We can do very nice calculations and so on and so forth. And so from that, this can be a nice reduced quantity. We have that the single particle density, if we want to include a little bit more information into the system. So this is then a density matrix. So then we sort of get, well, what is the sort of fractional share between two different orbitals in the system? So we can have a little bit more granularity about what's going on, but we haven't added so much information that we can't perform any computations anymore. And so lastly, at least in my simple list, this is no way exhaustive, we could also look at the single particle Green's function. And so this, of course, contains more information. It contains more about these single and two particle type correlation functions. But at least it's a nice starting point for other calculations. And so we have these sort of three objects, but they each have their own difficulties. So specifically, if we want to make approximations for the density itself, so a density functional, because that's effectively what we're doing, we're going to be generating that our observables are a functional now of some reduced quantity. And now the difficulty in deriving these different approximations is quite hard, because we've sort of reduced it down so far that it's now very tricky to develop different approximations. And as we'll see, that there is no constructive sort of recipe for generating new approximations. And that's the difficulty. However, because it's just the single particle, the numerical effort, so any computational implementation or the resources we need to throw at the problem is actually quite minimal in the grand scheme of things. And this is actually why density functional theory has turned into one of the most impactful computational tools spanning chemistry, physics, and material science. It's because it is very, very easy to implement. And this is very good for sort of total energy, just to give an idea of what types of properties we're thinking of here. So this is total energy, crystal formation, so on and so forth. So next here for the density matrix, well, it's mostly intermediate. It adds complications in terms of numerics, but because it has a little more flexibility, it's a little bit easier to develop approximations. And these, like I said, it captures the generacies, and so it's good for correlations in some sense. You can start to really have more granularity about how different orbitals talk to one another in the system. And then we have the Green's function, which is the opposite of the single particle density. It's very easy to derive various different functionals, which I'll show some of that tomorrow in my next talk. That it's very, very easy and very constructive to build different approximations. It becomes very, very hard to implement though. That you can have very, very strong numerical challenges that you have to overcome, and they take up a lot of resources to be able to perform these calculations. Like I'm sure you've seen with other speakers talking about DFT and these other sort of methods, that this becomes very, very computationally demanding in some aspects. But because now we have information about excitations, this is very good for spectroscopies. And so this brings in a lot of new information to try to model experiments in conjunction with our theoretical calculations. And so these have a really strong place in sort of our toolbox of things. But for today, I'm going to just concentrate on the single particle density, because this is what density functional theory is based upon. So, as I said, density functional theory is one of the most impactful methodologies probably in the 20th and now the 21st century. So the burst of density functional theory happened in 1965, and this is just showing sort of the citations of the first paper here, the Honenberg-Cohn paper, the Cohn-Sham paper, and some key articles that bring about different density functionals, as we'll see later. But the real point here is really to show this exponential growth in the citations per year of these various different papers. And so this methodology, there was a lot of sort of development that happened in the 70s with developing the various different codes that we need to be able to solve the single particle Schrodinger equation for a different material. But once we have these different codes that I pointed out here, then we really start to see this exponential growth in just the prediction of new materials. So, and also the materials genomes started using density functional theory to be able to bring about searches and predictions of a wide array of different materials with various different properties. We have the prediction of a superconductor. We have the prediction of also topological materials. And also in the materials project, as of April, when I made this, there was at least 750,000 compounds that have been calculated to date in their database. And so this is a very, very powerful method that started all the way back in the 60s and now is really the workhorse of material science and physics. And so this is really to show the impact before we start jumping into the nitty-gritty here. And so it's quite applicable to many, many different fields. So let's now see what is the beginnings of density functional theory here from the foundational standpoint. So the main idea of density functional theory is that we don't care about any of the excitation energies, two-point correlation functions. We don't care. We just care about what is the ground state energy of the system and what is the corresponding charge density, the single particle density for that ground state. That's all we care about. We don't have anything else on mind. These are the only two quantities we want to know. And this is already a very big step. And so to do this, as we've seen in our normal sort of quantum mechanics courses, we know that the ground state energy of the system itself for any Hamiltonian is, well, you can be determined variationally by sort of minimizing some choice wave function. And so we know this to be true. So since we know we have this many-body Hamiltonian, we can break this up. We can break up this problem into an object that depends on the kinetic energy and the electron-electron interactions, and that which deals with the potential from the material itself. Because we know we have the different atoms that are sitting in the lattice. They have their own potentials that they're generating that the electrons can sit in. And so this is then defined by the material or the atomic arrangement. But this here is a universal functional. This here is the universal part that describes every property of the electron that's sitting within the material. And here we can see that this is really just dependent on the density then, this ground state energy. So here we're going to assume that we take the wave functions, that it's going to give us a specific density. It could be any density, but it gives us a specific density. It's really just to make sure that we have a proper density that's sitting here. And because this thing has been split up, we have some universal functional that's here that describes all of the many body properties. This has everything that's hard. So we're essentially splitting this problem up into something that's easy that we can accomplish and throwing all the hard stuff into a simple object that we can perform all the approximations on. So when we do this, we perform then a minimization over all the different densities that this wave function can give us. If we then minimize over this object, we then are able to find the ground state of the system. So of course, this seems like a little bit like black magic, that we've just sort of formed some wave function. We want to find the ground state. We separate this object, and we take density to be the main key functional here, or the main object that we're minimizing against, and then we find the ground state energy. But it is really that simple, essentially, that we can separate this problem into something that's universal and something that depends on the atomic arrangement. But the key that we've gained from this is that we've also gained that if you solve for the potential here, which you could solve around and move this equation, you could solve for the potential. The potential then itself also depends on the density. So really what we've done by the Honenberg-Cohn theorems is that we've said for some external density here, we can derive some wave functions, As we then do the minimization process to get the ground state, we then find the actual ground state wave functions, which give us a very specific density. But that density itself implies a certain potential. So really what we have is the existence and sort of the uniqueness of the density for a given potential. So what we're saying really is that if we have some potential that's built up of the arrangement of atoms, we know that there is a particular density that gives that ground state. So what we're trying to do is think about, well, if you have some iterative process, if you want to solve this problem, but you want to know that the ground state has a unique solution, that's what this is telling us. This is saying that for a given potential, we have a given ground state density. And also vice versa. If we have the density, we also have a specific potential. And so that's all that we've done, is that we've tried to make this clear connection so that then maybe we can search for this ground state density and then ultimately the ground state energy of this many-body system. And this is purely for the n-electron system. So this could have 10 to the 23 different electrons in the system, and this same process holds. If we have the single particle density, it implies a potential, and also vice versa. And therefore, then it gives us some hope that we can form some process or iterative process to find this ground state density and ultimately solve for the ground state energy of this system, which is a very powerful tool since this deals with an infinite number of electrons effectively. So now that we have this process and at least this key result, well, this doesn't really help us yet because this isn't anything that hasn't told us anything constructive. It hasn't told us how to actually solve the problem. It just tells us, well, there's something that's universal. This is where we can make all approximations. And this piece here tells us that we can endow this with different atomic information. But we need to make this tractable now. We need to be able to solve this problem. And so this is where formulating some kind of auxiliary system helps. And this is called the cone-sham auxiliary system. And so what is it doing? So the main ansatz that they make is that, well, we have this uniqueness between the potential in which the electrons are sitting and the single particle density that they form. So the idea is then, well, what if we have some potential that mimics that many-body potential, but it's only a single particle problem so that we can solve it. It's something that's non-interacting. And that's exactly what this sort of cone-sham ansatz is that let's say we can have that the ground state energy for the many-body problem is given by a non-interacting problem, something we can solve. So essentially, we're going to assume that this mapping exists, and we just need to figure out what this potential is here, this V that's sitting in the corner. And so that's what this main thought process is about, taking the many electron problem, where we have all the mutual interactions of all the different electrons, and mapping it onto a system with just a single particle and some effective density. And we can all solve this problem. It's exactly like solving the hydrogen atom. It's just we have a very fancy then potential, which is then embedding all of the many-body information into it. And so this then will turn into an effective Schrödinger equation. So here, the main problem turns out to be, what is this potential? What potential gives us the same charge density as that for the many-body problem? And so there's a constructive way actually to do this. And let's see this. So here, we can construct what we call the cone-sham energy. So this is just going to be the total energy of the system. And we know that it's built up of multiple different parts. We have the non-interacting kinetic energy, because remember, we want to map this many-body system to some single particle system. And then we also have the external potential from where all the atoms are sitting in the crystal. We have the sort of regular Coulomb interaction, which because we know it, we can throw it in as the original ingredient. And then we have everything else that we don't know. And we're going to call that the exchange correlation energy. So this will then have all the other ingredients from the many electron problem that we don't know. So we're essentially isolating the thing that we want to approximate. And so this object here you could say the difference between that universal object that we found in the previous slide, and we're going to subtract off sort of these key ingredients we already know. We know the single particle kinetic energy, and we know this Hartree energy that's given above. So we know these things. And so therefore, this has to be everything that's remaining. And so this is the main object we're going to put all of our approximations. Now, if we perform this minimalization process on this total energy here, so essentially we're going to vary the wave function star, essentially taking just a derivative, we end up here with an object which is an effective Schrodinger equation that's given here. And so this cone-sham potential that I've listed here is that potential that will return to us the total energy and the single particle density for the many-body problem. So this is that effective potential that is endowed with all this extra information. And here you can see what's exactly input is. So we have here the potential is built up of wherever the atoms are sitting, this Hartree potential, and then the remainder that we have to figure out. This then lends itself quite easily numerically, and there's many different codes then that solve this problem. There's VOSP, which is sort of the standard for doing these first principles, quote unquote, calculations. There's a Green's function-based code, SPR-KKR, and also VEAN2K, which is an all-electron code for performing this task specifically. You're just solving this Schrodinger equation. That's all we're doing. It's just that the potential is very, very fancy in some effect. So this is where we've headed. Just as sort of a recap, we've taken the many electron problem we couldn't solve. We tried to solve it with orbitals. That didn't work. And then we found, let's pick something simple like the density. And that allowed us to move forward and at least be able to isolate an object we can approximate. And so, of course, the next question is, well, how do we approximate this thing? And so, ever since the sort of origination of this methodology, there's been a whole train of different functionals that have come about. This is in no way exhaustive since there's many, many different functionals. This is just to show the key different iterations of these approximations to this object. And so we have that Cone and Sham were the first to develop this sort of local density approximation. So here we're only going to include one ingredient, that this functional just depends on the density itself at some local position in space. Then people said, well, the density itself has some sort of modulation in the density. And so maybe a better description of this is actually taking into account also its derivative or its gradient. And so people came up with what's called the generalized gradient approximation, which now includes two pieces of information. One is the density itself, and then also its gradient or its variation in space, because it gives you semi-local information about how it's varying. And this then gave way, of course, to many different functionals. And PBE here, Purdue, Burke, and Ozanov actually is the workhorse throughout material science, chemistry, and physics. This is the main player in terms of the functionals that's heavily used today. We then had the idea, well, what if we added other ingredients? You can add the density, the gradient, and also a new kinetic energy density that we give here, which is just the gradient of the orbitals themselves. And so essentially we're adding more and more information. And so now there's sort of 3 degrees of freedom in describing this functional. You can have different hybrids, and that means we can add in some exact exchange. And then we have that within this family of meta-GGAs is the scan functional I'm going to talk about particularly, because we found that it is giving very, very good performance across a whole family of different materials. And then we also have hybrid meta-GGAs, so on and so forth. So this whole family of these things, but they can be organized in a very simple way. Namely that if you have one ingredient, the local density approximation, you're on some first rung to achieving chemical accuracy or the heaven of chemical accuracy. The generalized gradient adds in some semi-local information based on its neighboring potential because we're taking the gradient. The meta-GGA, as I said, takes in the kinetic energy, so we're on the 3rd rung. Hybrids are exact exchange, which are given here. We add in more non-local information. And RPA-like includes sort of these unoccupied orbitals, and everything gets much more complicated to calculate. So technically, this is the most computationally efficient. And as we move up the ladder, it gets more and more heavy to calculate, even though the accuracy becomes better. And so this is sort of the main organization of these different functionals that people have developed. And so the main issue, though, is that many of these functionals have different shortcomings, that they have a hard time in describing certain materials or certain types of bonding that's happening in the system. And so people then have developed new functionals and they obey different constraints. But really, what really should happen is that some kind of functional should be able to be transferable across a wide variety of different materials. And so if we really have a functional that is truly describing this many-body system, we want to be able to describe a whole bunch of different materials in different environments. Then we know that we have a functional that's really working and fully describing the physics of the system. And so at least to date, except for exception maybe scan, no conventional density functional theory is able to reasonably achieve accuracy for these different chemical environments simultaneously. So we have covalent different bonds. So you can think of like silicon or this H2 type molecule binding. We have metallic type environments where of course we can readily give up electrons, and so you can think about silver. We have ionic, so we can share electrons between different atoms in the system quite readily. Hydrogen type bonding, which is quite weak, and also van der Waals intermediate range type binding, which is even weaker, because these are based on sort of the electronic dipole fluctuations in both atoms that actually tend to pull things together. And so currently no functional is able to tie all these things together in under one description. That you have some functionals that work well maybe for these type of bonding environments, but not for these. And so it's really hard to span these different environments. And so the main idea or the main finding that we have for SCAN is that this new functional that we're going to describe is that it's able to adequately and very flexibly describe these different environments and really work across these different bonding type arrangements and give an accurate description chemically. And so it's a very powerful then technique where then we can describe everything from covalent to van der Waals simultaneously within the same functional. Assuming you can see the slides here.
That's right.
Okay, perfect, good. Okay, so where I was is sort of there's no functional that can really span these different bonding environments, and really to give an example of that, it's due to sort of these fundamental limitations in the construction of the functional. Namely that they have to obey certain constraints, but at the various different approximations of this sort of Jacob's ladder that I described, that they cannot be obeyed. And so we have the LDA approximation here. Since it only depends on the density, there isn't much flexibility in how it's constructed and how it's fit to the electron density. And so here it overestimates the binding energy, underestimates bond lengths. And so these are sort of key things that people have noticed. For GGA, turn my pointer on again here. And so for GGA, which is now including that little bit more information of the gradient, it seems to now overcorrect things. Now it underestimates bonding energy and overestimates bond lengths. And so we've sort of shot too far. And so both of these sort of fail to capture the different correlations in the materials. And the real fundamental problem is that it's very hard to satisfy different exact constraints that we know mathematically should exist on this functional. And so like, for instance, here we have that a GGA cannot satisfy the uniform electron gas. Specifically, if this a function here, f of x of s, equals 1, and it has to be less than 1.74 because somebody has solved this bound for a 2-electron system. But it cannot simultaneously do that while maintaining this other bound here, that it must be that the exact functional has to be greater than 1.174 times the LDA total energy. So these are two contradictory facts. And so by looking at exact constraints of the density functional itself, that then you can start to see where different functionals cannot adhere mathematically, and so they're fundamentally limited. But the key here to recognize is that the more ingredients you put into the problem, the more flexible it becomes, the functional itself, And so the more you can adhere to these different exact constraints. And so by doing this, that's why the meta GGA, where we add in this kinetic energy density, makes itself quite flexible and amendable to doing this. And so here, the extra ingredient is this kinetic energy density, and it can start to describe different environments. And so here, this tau here is that density. And we're going to have some indicator, this alpha, that recognizes different chemical bonds. So it can recognize the uniform electron gas over here. And we have actually the analytic formula for that. And we can also describe these sort of two bonded different, or these two closed shell different atoms here, the hydrogen and the helium. And here the alpha ranges between 1 and 0. And these are known forms. So we have here this tau Weizsäcker is given here, and the tau uniform is given here. So by analyzing between 0 and 1, and also things that are greater than 1, we're able to recognize the different chemical environments in the material. So specifically, for single orbital or covalent type bonds, we have that tau equals tau Weizsäcker, and so it's 0. If we have a slowly varying density, so we have that tau is then very close to a uniform electron gas. And so then this alpha equals 1. And if we have the overlap of closed shells, so you can think about the space in between the levels of an atom, this then gives us an alpha, which is actually very, very much greater than 1. And so because of this then, we're able to identify these different environments. And so we can construct then a GGA, a specific GGA for each chemical environment, and then make sure we can interpolate between them to really to construct the full functional itself, to be able to be transferable across all these different environments. And so this is where we're heading. And so that is exactly the type of functional we want. Something that's able to identify where it is and be able to then have a specific functional that will give us the correct or an accurate description of that environment itself. And so this is then the descriptor we're going to be using. And just to give one little consequence of this is that it actually changes our effective Schrödinger equation. So like before, we saw that, well, now we're going to be solving some effective Schrödinger equation. It has some potential from where the atoms sit. It has the Hartree term, and then this effective potential that has all the many-body information that we're approximating. So this is the usual scheme that we have. But now when we add in this tau, this extra information from the kinetic energy density, we actually get a new term. We get this term that's over here, and this is non-multiplicative. So in the sense that here you could separate out the sort of the operator from the wave function, but here you can't. It's built in to this object here because of the derivative operators and because of this potential of tau. And so here you can actually start to see we gain new insight into the chemical environment also at the level of the effective Schrödinger equation that we're solving. We now have something that actually includes like a spatially dependent effective mass. Because if we then carry out the gradient here, we're going to have one term that gives us the grad squared times the orbitals with this potential. And that is the same as this kinetic energy with some effective mass that's actually changing as you move throughout the material. And so really this functional is giving us some very interesting new insights into how this density is changing and then changing the effective Schrödinger equation also concomitantly. And so also due to this fact, we have that the band gaps within this scheme are actually very good. That actually they are now guaranteed to be the fundamental gap of the material. In the standard cone-sham-based DFT, they're not guaranteed. But once we add in this effective mass term here, or at least we add in this extra information, we now get good band gaps from our theory, as we didn't before. And so this is a part of the framework that's now being built up to be able to handle this new flexibility in this functional. And so just to speak quickly about the particularity of this scan functional, we have that it now obeys all 17 exact constraints that a semi-local functional can. And so this is new and improved. So like the issues I mentioned with GGA and LDA, that they had these intrinsic limitations based on the fundamental mathematical structure that this functional can have. And here, this obeys all 17 known constraints that we have. And so it's very well put together. There's different appropriate norms, meaning that we like to talk about the uniform electron gas, hydrogen, and helium. The main sort of idea behind using these as sort of objects to normalize against is that these are really transferable physics objects that we know at least the physics that's contained in these exist in many, many different physical systems. And then we're not choosing maybe certain sets of molecules or certain materials to sort of fit against. We're choosing something that's more universal and more sort of physics-based in that sense. And this is then just describing that our construction for this sort of interpolation based on this alpha parameter that really tells us what type of environment we're sitting in. And this then allows us and gives us the transferability of this functional. And so the main characteristics about this functional, just to mention, is that it's non-empirical, it's useful, reliable, and predictive. And so if there's anything else you don't remember from this, that essentially this is not empirical, and we found that it's very reliable and predictive across a wide variety of material families. And it's really because we add in this new ingredient into the functional. So just to give an idea of its improvement, that this has been used for covalent and metallic bonds in silicon, ionic bonds in this manganese compound, and weak bonds in ice. And we see here that the scan results, which is given in green, are matching those from higher level functionals like HSC, but also diffusion Monte Carlo. And so these are comparing excellently with very heavy, very accurate calculations of Monte Carlo. And we're accurately describing both silicon configurations simultaneously. For the ionic bonds, we can see here scan is given in the blue. And for at least the experimental data that's given, it's very, very accurate. But then it also follows what we see in at least other experiments of sort of maybe not so high quality samples, where we can't get a clear experimental value, but at least it's following the trend of what we expect. And the main part is that we're really getting this beta phase of this material correct. And then for ice, since we have so many different bonding environments, we have that scan is actually following very, very nicely to these more heavy functionals with PB in this van der Waals. And so overall, we see a very high degree of transferability of this functional across many different families. And so the main idea here that we took away from this study is how does scan perform on strongly correlated materials? And so we really want to shine new light onto some old problems to really see how well and how far we can push this farther without sort of incorporating these different sort of parameterized many-body calculations. And so just to introduce the cuprates a little bit, as I mentioned, they were found in 1986 by Bernoz and Muller. They are a high-temperature superconductor. And so, of course, there's a lot of vigorous activities surrounding them, because if we can figure out its mechanism and maybe how to predict, we may be able to get a room temperature superconductor, which would represent a very large technological advancement. And so, as I said, this material is an antiferromagnetic insulator in its parent phase. As we begin to dope it, you can start to see superconductivity appear. But there's also many other interesting effects that also happen. There's sort of a melting of the spin order, and you can also get stripe-like effects. You can get charge density waves, and also the crystal lattice changes between these different electronic phase portions of the phase diagram. And so really what we see is a strong correlation and entangled degrees of freedom between sort of charge degrees of freedom, possibly these charge density waves, magnetism itself, and sort of forming either stripes or fluctuations of the magnetism, and then also the lattice. And so we can have different distortions that appear as we start to dope the system and look at these different other electronic phases, that everything is wrapped up together. And it seems to be also concentrated around where we see superconductivity appearing. And so all these factors seem to be playing a role into possibly setting the environment in which superconductivity emerges. And so that's why it's very important to then get correct what normal state the superconductivity is appearing from. And so that's going to be the main question of this study, is how well does this scan functional reproduce the different pristine properties of this material. And so first off, let's see what has been done previously to compare our work against. And so if we look at the cuprates within density functional theory, so these quote unquote workhorse functionals, so LDA and GGA, we see that, well, with LDA, we can't even reproduce the antiferromagnetic band gap. We have that the density of states does not illustrate any gap, and the magnetic moments themselves are quite small. And we also get an incorrect structure prediction. And if we look at the GGAs, we have that there's a very, very small band gap, so it's slightly insulating, but not too heavily, because we're expecting around this 1 eV band gap. And the moments are about half the size that they should be, but the structure has gotten better. And so we don't really have a good description of this material, but at least it's getting a little bit better in GGA, but we're still not there. And so this was seen as a very big failure of density functional theory, that it could not predict the parent properties of this material. So then people went forward and said, okay, what about these different hybrid functionals? So they find, oh, we find something very good for the pristine material. We get an antiferromagnetic ground state. It has a 2 eV band gap, which is quite big comparatively, but at least we're getting a gap, and we get the antiferromagnetic ground state. However, if you start to dope this material, it still stays insulating. So we can see that it does not turn into a metal, and if we dope further, it's still not a metal, even as we dope quite higher with these different rare earths. And so again, density functional theory in some way fails, because as we dope the cuprates, we would expect it to become a metal. We would expect that you're removing a little bit of electrons from the system, and the Fermi level should just drop down and cut through the bands. And so this, again, is doing something very strange and showing a real big disappointment in terms of density functional theory. So that then led us to performing other sort of beyond DFT type methods. And so specifically, we have schemes that are either like LDA plus U, quasi-particle GW, DMFT, which you've probably heard in some previous talks, and also two-particle self-consistent, which comes from the group of Tremblay up in Sherbrooke. And they all follow sort of a similar process. This is actually for the DMFT self-consistent loop, that you start with some kind of DFT ground state. You then able to extract the local Green's function, self-consist with some kind of impurity model to generate a self-energy effect, and then you can insert that back into the LDA results, and you can further charge self-consist if you want. And so if you indeed do these methods, you do get a nice gap. This is at least looking at quasi-particle type GW, and you can see, yes, it does become a metal upon doping, which is very nice, and we gain the antiferromagnetism. And this waterfall type effect matches ARPES measurements. And within also DMFT, we can see the same thing. It also becomes metallic under doping. The quantum Monte Carlo finds a very nice gap. And also the CD MFT also finds really nice results with experiment. But of course, the main problem that happens is in this, we've introduced some empirically derived parameter. And so we have this U parameter here that we've inserted to gauge the correlation strength. And of course, we can derive this from some ab initio methodologies like CRPA or something. But it doesn't necessarily, it's still effective, because what does it mean to have the Coulomb potential just be one number? And so we're still missing something. Otherwise, these methods do a very nice job on describing things. And so the reason for applying SCAN to this is to really see, can we get around this issue? Can we find an actual first principles way of doing this where we don't have to maybe have these parameters that are a little bit sometimes ill-defined or don't capture some of the physics that we want? And so this is what we want to ask. And so here, the simplest question to start with is, do we get the the structures of the crystal correct? And particularly their energetic orderings. And so there's 3 crystal structures that come out. We have the high temperature tetragonal, we have a low temperature orthorhombic, and a low temperature tetragonal phase that this crystal exhibits. And they all happen at different temperatures, and they happen at different situations in doping. And so the idea would be then, okay, are we at least getting these structures correct? And so here we show the difference in energy between the HTT and the LTO phase. And so if all the green dots are above here, which means that the LTO phase is winning, that's the ground state. And we can see here that at least energetically, that this makes sense with the transition temperature that we have from experiments. And so we hear that SCAN is doing very well to describe this structure. Now, if we look at the LTT phase, we pit it against the LTO, we can see that yes, that compared to LTT, SCAN is the only one that says LTO should be the ground state. And all these other functionals do not reproduce the correct ground state crystal structure. And so SCAN is doing very, very well in describing that crystal. As we then dope the compound, we know that there should be a transition from LTO to LTT type structures. And from this, we find that, yes, indeed, there is this sort of neodegeneracy of the two structures compared to most of the other functionals. And this is really describing the experimentally observed modes that they're finding, sort of these mixtures of different orbital configurations within the crystal once you dope the compound. So here we can find, at least from the lattice standpoint, that the functional is doing very well in describing the ground state. So now the question is, how are we doing on the electronic side? So we have here that I've given data for the band gap, the electronic band gap, for all the different functionals that we've tried. We tried 13 different functionals, and here we have SCAN particularly. And here I've also listed the different crystal structures. And this is the corresponding band structure for SCAN also, so we can begin to see what it looks like electronically. And so here, looking at the band gap, we have very good agreement with the different experiments, particularly the optical experiments that were done. We find that we're in almost perfect agreement with the 1 eV band gap. There's some other variations of SCAN, which are actually quite smaller. There's a couple other meta-GGAs that do reasonably well. Otherwise, the other functionals that we've tried perform very poorly, including the HS. The slides, right? Just to make sure.
Yep, that's right.
Okay, good. Thank you. Okay, so the main point here is that SCAN does a very good job in getting the band gap correct. This is then compared to experiment. If we have the optical spectrum here for zero doping, yes, there's a peak in the spectrum, but what actually matters is the leading edge. And so the leading edge SCAN caps the gap. And this leading edge is very important because it's the infinitesimal, it's the distance that the electron can just hop across to be able to generate this excitation. And so that is particularly the band gap that you're seeing in optics. And so this also agrees with different transport measurements. And then I've also listed various other theories, PB0, B3 Lipson quantum Monte Carlo, and all their data is quite above the experimental results that are given here. Just to mention, this is what the density of states looks like. We can mention what that peak is, and that peak looks like it's some D to D transition in the optical spectrum from our theory. If we then map this onto effective U and Hund's J parameters, like you've seen in the DMFT, we get about 4.8 and about 1.2 estimations for these, which is right on with the other calculations that have been performed in the literature. If we then look at the magnetic structure, just to save time, the upshot is that we do stabilize the magnetic ground state. We find magnetic moments that are consistent with the experimental results, and that's then seen, of course, here compared to all the different functionals. We additionally find a small moment on the apical oxygens, and importantly, we also get the correct orientation of the moment, that it's in the plane and pointing anti to the bond arrangement. And so this is in exact agreement with the experiments. We've also then calculated the effective spin-spin interaction within this system. We get that it's about a negative 138 MeV, and then also the experiments are on 133. So overall, we see very, very good agreement. Just to show what the magnetic densities look like, this is then the density. So the upspin here is given in yellow, the downspin is given in blue, and we can see it alternates between the layers following the magnetic arrangement. And we can also see some of these slight out of plane apical oxygen magnetization also. But the key point here is that the magnetic form factor we calculated, this blue line from this density, matches the experiment quite well, given here by the red dots. So what we find is then some holistic picture of both the crystal structure, the electronic properties, and the magnetic properties for this material simultaneously, without the needing of any external parameters to correct various different properties. Now, the main issue also was about doping. And here we also performed a doping study, and we find that as we dope the material, it does indeed become metallic. The gap shrinks a little bit due to the magnetism, but overall, we find very good agreement again with what we find characteristically with experiments. And so this is what we found for LCO, sort of this prototypical high temperature superconductor. We've then gone beyond this material and looked at a vast array of other compounds that are correlated, specifically the new infinite layer superconductors made of nickel, also the strontium iridates. We've also analyzed that and found its different magnetic moments and such are in good agreement. Looking at other high temperature superconductors, this time layered, the YBCO compounds. Battery compounds are also well described. Other 3D perovskite oxides in general, ferroelectrics, heavy fermion compounds, and also these very complicated magnetic structures that just originate within pure manganese. And so overall, we have very, very nice work showing that this functional is really actually giving us some new information and also giving us a holistic picture of these different materials, even though that they're correlated. And so just to finish out with some key points is that after describing density functional theory, the upshot is that in principle, we get an exact total energy of the system and the single particle density. This is what we gain from the theory by only knowing this exchange correlation functional. And of course, this is in practice something that's approximate, but we've seen that by constructing these functionals in a very methodical way, we get something that's fully translatable across different bonding environments. And this is also a unique method for solving the many-body Schrödinger equation. But this is its own path to solving this problem. And so also due to the balance of accuracy and computational efficiency, this is why DFT has become one of the most widely used tools in computational physics and also physics, chemistry, and materials science. And as I just stated, SCAN does a very good job with these correlated materials. And this then opens up a pathway for examining the electronic structure and phase diagrams of other complicated materials in general. And so for any sort of references or lecture notes or textbooks that are related to this area, I have them up on my website. If you go to cluster353.net/GW, and I have a whole list of different references and also hands-on tutorials made for like the open source code Quantum Espresso. And so people can try out density functional theory for themselves. And with that, I'll thank you for your attention. And I'm sorry for the glitches along the way with this internet connection.